You know that feeling of looking for a needle in a haystack? Well, in computing, that's not just a saying, it's a massive, everyday problem. Today, we're going to talk about Grover's search algorithm. It's a truly mind-bending quantum solution that finds that needle way, way faster than any regular computer could even dream of.
So to really wrap your head around this, just picture a phone book. A huge one with a million names. But here's the catch. It's a complete mess. No alphabetical order, nothing. Total chaos. And your job is to find one specific name. I mean, where would you even begin?
If you're using a normal computer, or, just your own two eyes, there's absolutely no shortcut. You've got to start at page 1 and just grind your way through, name by name, until you stumble upon it. And the worst part? It could be the very last name on the very last page. Talk about inefficient.
Right, so this is what we call the great search problem. Let's break down this difference between the old-school, painful classical grind and the, frankly, unbelievable leap that quantum computing offers.
Now, don't let the fancy letters here scare you off. It's actually pretty simple. The classical way is called O and N. That just means if you have n things to search, it could take you up to n tries. A million items, a million checks. But look at the quantum approach, O and square root n. That little square root symbol, that changes everything. Instead of a million checks, you're now looking at closer to 1,000. This isn't just a little bit faster, it's a completely different ballgame.
So how on earth does a quantum computer pull this off? Well, the first secret weapon sounds like something straight out of a video game. It's called the Quantum Oracle.
The best way to think about the Oracle is as this magical black box. You have no idea what's inside, but you know it has one amazing superpower. It can instantly recognize the right answer out of all the possibilities. Its job isn't to tell you the answer, but to secretly mark it for the next phase of the plan.
And this is a really crucial point. The Oracle doesn't just hand the answer over. That'd be too easy. No, it does something much cleverer. In the quantum world, all the possible answers exist at once, each with a certain amplitude. The Oracle finds the right one and performs a trick. It flips its amplitude, basically sticking a negative sign on it. It's like it taps the right answer on the shoulder and says, "You're it," without telling anyone else.
Okay, so the Oracle has secretly flagged our answer. Now we get to the real heart of the algorithm. This is where the magic kicks into high gear. We have to take that tiny, secret signal and crank up the volume until it's impossible to miss.
This whole process is like a two-step dance. We do it over and over. Step 1, the Oracle flips the sign. Step 2, another cool process called the diffusion operator comes in and uses some clever math to boost that one item that just got flipped. Let's actually see what this looks like.
So, before we do anything, our quantum system is in what's called a superposition. Just think of it like this. Every single possible answer is on the table, all at once, and they all have the exact same tiny chance of being right. You can see it here on the chart. All the bars are the same height. It's a perfectly flat landscape. And now, the Oracle makes its move. It finds the one bar that represents our correct answer. But watch closely. It doesn't make it taller. It does the opposite. It flips it completely, making its value negative. All the other bars, they're left exactly as they were. And there it is. You can see that one bar is now pointing down, below the line. Now, this might seem like a small change, but it has a huge consequence. It actually pulls the average height of all the bars down just a tiny bit. And that new average? Well, that's the key to the whole trick.
Here comes the genius part. The diffusion operator steps in. You can think of it as inversion about the mean. It treats that new average line like a mirror and reflects every single bar across it. And bam! Look at that result. The one bar that was negative and way below the average gets flipped way, way up, making it massively taller than anything else. And all the other bars? They were just above the average, so they get flipped to be just below it, making them even smaller. We've just made the right answer scream out from the crowd.
So this two-step dance gets repeated over and over. Each time, the correct answers bar gets even taller and the wrong ones get smaller. But what does this actually mean in the real world? How much faster are we really talking?
Okay, let's go back to that phone book from hell, the one with a million jumbled names. We already know the classical way is a complete nightmare. So, what can Grover's algorithm do?
And here it is, the big payoff. A classical search could take, in the worst case, 1 million operations. But with Grover's, we only need to run that little two-step dance about 785 times. Just let that sink in for a second. 1 million versus 785. The difference is just staggering. It's almost hard to believe.
That, my friends, is exactly what we call a quadratic speedup.
It's not just an improvement, it's a revolutionary leap that completely redefines what is even possible when it comes to searching for something. Okay, this is all amazing in theory, right? But what about in reality? Where does a tool this powerful actually make a difference? What's the so what here?
Well, the potential is just enormous. Think about cryptography. This could be used to brute force passwords, which is a little scary but powerful, or searching massive, messy databases for information. It could even be used to find complex patterns in data for things like medical diagnostics or financial markets. The list goes on and on.
But let's be clear, it's not a silver bullet for every single problem. Grover's algorithm is the undisputed champion when your data is a total mess, like our phone book. But if your data is already nicely sorted, a simple classical search can actually be faster. It's all about using the right tool for the right job.
So, when you boil it all down, what's the big takeaway? Grover's algorithm doesn't just make searching faster. It fundamentally changes the rules of the game for a whole set of problems that have been bottlenecks for computers for decades. It's a whole new way of finding things.
And that really leaves us with a pretty mind-blowing question to chew on. If a quantum computer can turn a million-item search into a walk in the park, it just makes you wonder, what other problems that we think are impossible today are just sitting there, waiting for the right quantum algorithm to come along and crack them wide open?